This is part 1 of lecture 8 on fading, diversity, and coding. Just to remind you what we were before, in part 2 of our lecture series, we had like 4 lectures on channel modeling, and if you want to summarize that in a couple of things, couple of slides, we said that when you have like a base station in here and a mobile is moving away from that, power starts to fluctuate like this, up and down, and we refer to that fluctuations as like shadow fading, and that was the changes on the average, and instantaneous changes was like Rayleigh fading. Okay, and then if you look at one of these points that I have so much power, if I look at channel impulse response, I have a channel impulse like that. At the beginning there is only one path, and when I go away I have multiple paths, and finally at certain time I have a number of paths, and first path is not necessarily the strongest path anymore, and this is the time that there is something between transmitter and receiver. We refer to that as obstructed line of sight. But that was about characteristics of the channel. And then we said that if you want to look at that and now take this channel and use it for a modem, because part 3 of our lectures is related to design of the modems. If I want to design a modem, basically these characteristics can be classified in 2 different things. One is characteristics which are related to wideband communications, and characteristics which are related to narrowband communication. And if you remember, narrowband communication was the time that your symbols were like a slow related compared with a spread of the channel. Means that if you take the RMS multipath spread of the channel and inverse it, your symbol duration is like 10 times more than that, for example. Then all these paths, I mean, you send a symbol and like many paths are coming, but they come on top of one another. And what will happen is that like if you have like you have 1 over tau RMS, I mean, if your data rate, your data rate is like less than like 10% or 20% of 10 to 20% of inverse of tau RMS, if your data rate is like that, then your pulses are wide enough so that if you have multipaths are close to one another. They come right on top of one another, almost very close on top of one another. So what will happen is that you have like this phasor diagram, and they add to one another, if you remember, and this would be magnitude of the total. These are magnitude of each of these components. So in narrowband communication, really what I send a pulse for my communication. It arrives from different things, but still I have one pulse with the same shape. But since these guys, they have different phases like this, they add together, and this total amplitude of all of them together fluctuates up and down like this, which we called it multipath fading. Okay, that was narrowband communication. But in wideband communication, what will happen is that if these are paths of the channel, impulse response of the channel, but my communication is something like that. So I send this pulse, arrives like that, then arrives like this, then arrives like that. So I have sent a pulse like that, and I receive a pulse like this, for example, which is much longer than what it was transmitted. So it causes intersymbol interference, and intersymbol interference causes a lot of problems. Okay, so we have like narrowband communication, wideband communication. For narrowband communication, we are only interested in amplitude fluctuations. For wideband communications, we are also interested on impulse response of the channel. Now, if we come back to the computer, so we have 2 characteristics. We have impulse response of the channel, and we have fluctuations of the amplitude like this. For narrowband communications, we are only interested in variations of the channel. For wideband, we are also interested in the impulse response of the channel. Okay. Now we have a bunch of modem design technologies, and we talked about overview of those modem design technologies in lecture 7. Okay. Now we want to see what is the effect of this fading characteristics on them. In lecture 7, we are looking at the effect of narrowband modems, effect of fading on narrowband modems. In lecture 9 and 10, we talk about effect of multipath structure on wideband modems. Okay, that's basic. But before I go there, just I wanted to refresh your mind about one more thing. This was the story. My overall channel response was something like this. In this direction was angle of arrival, and in this direction was delay of arrival. So I have a bunch of impulse responses as I move from a location to the other location, and each of these impulse responses really in each location can be different impulse responses from different angle of arrivals. So it's a two-dimensional function. If I stay here and I put my transmitter in another location, I have a two-dimensional impulse response. One dimension is the delay spectrum, the delay. The other direction is angle of arrival. And then when I get this type of like two-dimensional, I map them into 4 set of parameters, like beta and phi, which are magnitude and phase, and tau and theta, which are delay and angle. So I have a bunch of paths, path 1, 2, 3, 4, 5, whatever, up to path number L. Each of them have 4 parameters: magnitude, phase, delay, and angle of arrival. If I get all 4 of them together, I have an impulse response 3-dimensional like this. Okay? But I don't need all 4 of them all the time. If I'm doing like narrowband communication, I'm only interested in what? In envelope. And envelope is really magnitude and phase. Well, I'm also interested on angle of arrival. If I have like a MIMO receiver, or if I want to do a space-time coding. Okay. When I'm talking about wideband modems, I'm interested in magnitude, phase, delay, and angle of arrival. I'm interested in 4 of them. Lecture 7 is related to narrowband. Now, in narrowband communications, really what will happen is that if I don't consider the angle of arrival, I receive this 3-dimensional impulse response, and then if I just forget about angle of arrival, I have a 2-dimensional impulse response like this. Okay? And each of these paths, I can represent them by phasor like this, add them up together to something like this. This is what I'm using for narrowband communication. This is really amplitude fluctuations, changes of amplitude. And that's the only thing that I'm interested in narrowband communication. Okay? Now, so this is like an overview of part 2, like channel modeling. I didn't talk about that in lecture 8, because in lecture 8, if you noticed, I didn't brought the channel characteristic into the picture. I just talked about review of modem design technologies in general, and I told you that these are multi-symbol things which are used in wireless LANs, and this is GMSK and Pi/4 QPSK, which are used in cellular networks. But I didn't talk about channel characteristic and relationship between those two. In this lecture, I would like to relate them with the channel characteristics. Why do we want to relate it to channel characteristics? Because if I relate it to that, now you can understand what is the impact of fading and how you can remedy that by providing diversity and coding. And if you don't know that, you cannot. Okay? But, so, Basically, if I come now, part 3 of my lecture series, I have in there like 4 lectures. Lecture 7 was the one that I gave you last week. I just reviewed basic narrowband modem technologies. I told you what are the basic binary communication, what are the basic multi-symbol modulation techniques, and I introduced like system engineering approach. I'm interested in what? Signal constellation and how to relate it to probability of error. And then at the end, I talked about 2 important modulation techniques, GMSK and pi over 4 QPSK, as 2 popular narrowband modem technologies which are used in cellular networks. GMSK was used in GSM and pi over 4 QPSK in American IS-95 and Japanese digital cellular TDMA networks. So that was like introduction, but I didn't talk about radio channel characteristics and impact of that. This lecture 8 is going to talk about fading, diversity, and coding. That's the general topic. What we want to say is that we want to say, what does fading do? Okay, to my performance. My performance criteria up to now was probability of error, if you remember, and its relation to signal-to-noise ratio. But in fading channels, in real radio channels, signal-to-noise ratio is not fixed. It's changing. So how do I want to handle that? I have to change my performance criteria, and I have to change my equations, really, for calculation of error rate. So that's the first part of the thing. The second part is that I would start telling you a little bit about diversity and why it is important for fading channels. Indeed, the only remedy to fight with fading is the diversity, and I will show you why. And then I will talk about effectiveness of coding, why coding is effective, more effective actually in fading channels. And then at the end, I talk about latest interesting areas in here, which are space-time coding and MIMO. And I will tell you how they work. Without having the previous discussions that I had in here, you couldn't understand that. So this is the purpose of this lecture. Then, with the following 2 lectures, I will talk about, in lecture 9 in particular, I talk about equalization, smart antennas, and OFDM. And in lecture 10, I talk about spread spectrum and CDMA. Both of these are wideband, and these things, they can be wideband, they can be narrowband. But today I talk about narrowband version. So this is more or less what we want to study today. Now, to go further, again, if you remember from the last lecture, I took all of these modulation techniques that you have seen in other courses, and we just came back to like signal constellation and this thing. We said that always I have a receive signal like Z of t, which is the receive signal after match filter when I sample it at time t equal to t. And then this A sub I was the symbol which was transmitted, which is like ±1 or ±3, or depends on binary or multiple symbols. And then it can be a complex number if it is like what? Multi-phase, or if it is QAM. And then ES was energy per symbol, per basic symbol. Okay? Eta was the additive noise. Okay? So based on that, I told you that if the variance of this additive noise is N0, and the D is the distance, minimum distance, between 2 points in the constellation, like this 2 or like this 2, then you can approximately calculate the probability of error with this equation. And then using this approximation, sometime I derived a bunch of equations like this, which were relating, for example, probability of error to signal-to-noise ratio. And the signal-to-noise ratio per bit was what? Was gamma B was energy per bit divided by N0, which was variance of the noise. And then we have these equations for different modulation technique. This is for coherent detection binary PSK, and this is for non-coherent detection binary. And we saw that they are either in the ERF format or exponential format. And we discussed that, and we also sketched these so-called waterfall curves for all of them. These waterfall curves in here is probability of error in logarithmic form is 10 to the minus 1, 10 to the minus 2, minus 3, etc. In this direction is signal-to-noise ratio in the dB. This value in dB. That was where we were last time. But remember, my assumption was that my received signal is this thing, this Z sub t, which is some fixed number related to energy of a symbol multiplied with a number. And then I have some noise added to that. Now, what I want to do right now, I want to go to radio communication over flat Rayleigh fading channels. If you remember, we talked about variety of fading channels. Rayleigh, Rayleighian were the most dominant. Now, to describe the effect of fading, I only discuss Rayleigh fading because equations which comes up out of that are simpler. And meanwhile, Rayleigh, if you remember, is the most popular model. Then what will happen to the rest of the guys? For the rest, you can do these calculations. Often they end up to be like papers or something like that. So you can trace the result in the literature. And in reality, if you are interested in that, really you do just channel simulation and you simulate these things over the channel, real channel. So if you want to have some sort of closed form expressions, Rayleigh fading is very good for the analysis. And it gives you the idea, because our purpose is to develop some intuition. Intuition for what? Intuition for what is wrong with fading channels, and intuition for why diversity provides performance improvement, and having some quantitative numbers in there. And then why coding is so effective and so important. Okay, so I start in this first part. We are talking about 8.1 and about description of effect of Rayleigh fading on the error rate. That's what we want to do. So I have a modem. It has a probability of error which is expressed with something like one of these guys that I have in here, which is either an ERF function, or exponential function, which relates signal-to-noise ratio to probability of error. Okay, and I want to see what will happen if I have now a fading channel. If I have a fading channel, really, this received signal that I had in here is now the symbol multiplied with another number, a factor that I call it alpha. This alpha is a random variable representing what? Representing the fading. So my received signal is A sub I, my symbol, times alpha, which is fluctuations of the channel due to fading, a square root of ES plus epsilon. Okay? So when I was doing my calculations in chapter 7, my Z sub t really was also a random variable, but this guy was a fixed number in a sense, only changing with polarity of the symbols. Here, in addition to polarity of symbols, I have a random number which is multiplied by my received signal. Okay? And that's the representative of the channel. And that's the representative of fading in the channel. So I start with this thing. My receive signal is something like this in fading channels. If I take the effect of fading, I have this additional alpha. What is this alpha? This alpha is Rayleigh fading in our case, because our amplitude is changing due to Rayleigh. If you want to have a picture of that, this is the picture. I have this like fading channel. Everything is moving like that, moving up and down on the fade. If it was not a fading channel, I had like a fixed number like this for my signal to noise ratio. In here, my signal to noise ratio is changing. This is my gamma sub b that actually is changing. Okay? If gamma sub b, which is my signal to noise ratio, changing, it has an average, something like this. This is the average. I call it average gamma sub b or gamma sub b bar. This is average, which is fixed now. But when I was talking about performance in chapter 7, it was gamma sub b itself which was fixed. Okay, so I have gamma sub b, which is a random variable, and this random variable is changing according to Rayleigh distribution. Rayleigh distribution. What I want to know is that for a given value of average signal to noise ratio, what is my probability of error, or what is anything else? Let's look at the probability of error. If I look at the probability of error, when my power is going above the average, way above, probability of error is almost 0. When it comes way down, probability of error gets close to what? Close 0.5. Because situation is very bad. Okay? So, probability of error is also a random variable. But it's not a Rayleigh random variable. It's function of a Rayleigh random variable. And what I want to do is that I want to calculate that. Now, what can I do? Error rate is changing as the signal to noise ratio is changing. So I cannot talk about error rate. I have to talk either about average error rate or something else. That something else that people talk about is the so-called probability of outage. Probability of outage is that I assume there is a threshold for error rate, like let's say 10 to the minus 5. Okay? Anytime that my probability of error became under 10 to the minus 5, I say that I'm in the outage. And then what I do, I calculate the probability of being in outage. Means probability of being in here, or here, 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 here. So, when I come to the radio channel, effect of fading, and I want to consider that my simple probability of error is now changing to what? To two parameters, or two performance criteria. One is probability of error, average probability of error, and the other one is probability of outage. So let me just put it in here. In non-fading, my performance was what? Measure of performance was probability of error. This was a function of gamma sub b. When I go to the fading channels, any sort of fading, but the one which is my example is Rayleigh, my performance actually has two measures. One is average probability of error, means average error rate over all possible values of gamma sub b as a function of gamma sub b average, or gamma sub s average. The other one is the so-called probability of outage, which is also a function of gamma, the so-called threshold. Okay? So I have a threshold error rate. For that threshold error rate, P E threshold, I have a gamma threshold. And then probability of outage is probability of being worse than this situation. Okay? If you want to interpret that in terms of time, This is percentage of time that I go under a certain threshold. If you want to do it in the space, these are percentage of spaces in which I have a probability of error below the certain threshold. When we are talking about mobile communication, we have both time and space. Because if I go to different locations of a building, I have different error rates. So I find like 10% of the areas in this building doesn't provide good coverage for 802.11. That's probability of outage of 802.11 in this building. Or I can go like in a mobile. I'm going in a highway, and as time passes by, I want to see what is the average, what is the probability of going under acceptable error rate. So both time and space are my considerations. But mathematically, there is no difference. Now, to go there, now we go back to here to our calculations. So my received symbol that in the old time was z sub t without this parameter alpha, but right now it is multiplied with this parameter alpha, and this parameter alpha is that Rayleigh random variable. This is fluctuations of the amplitude. Rayleigh distribution function is like this. This is the Rayleigh distribution function for this alpha. How about now signal to noise ratio? What was my signal to noise ratio before? It was EB over N0. Now I have multiplied all my amplitude by alpha. If I multiply the amplitude by alpha, what will happen to the energy? It would be multiplied with magnitude of alpha squared. Okay? So my instantaneous signal to noise ratio is this thing. Do you follow that? Okay? So my instantaneous signal to noise ratio is the old signal to noise ratio multiplied with what? Multiplied with alpha squared. Okay. Alpha is a random variable, so gamma sub b will be a random variable. But previously, gamma sub b was a fixed number. Now, if I have this gamma sub b a random variable, and in this side I have a constant times another random variable, what is the distribution function of gamma sub b? It would be the distribution function of alpha squared, because constant doesn't change the distribution function. So gamma sub b is the distribution of the gamma sub b is distribution function of alpha squared, similar to that. What was the distribution function of alpha? Was Rayleigh. What is the distribution function of alpha squared? You remember that? Well, simpler than that, is exponential. If it's only one of them, is exponential, which is first order chi squared. Okay, so this is the distribution function, exponential, for what? For alpha squared. So that's the same for distribution of what? For the signal to noise ratio. So my received signal to noise ratio really has a if I have a Rayleigh fading channel, my received signal to noise ratio will have a distribution function which is what? Which is exponential. It's something like this. So the highest probability is in here, okay, for gamma sub b equal to 0, and then the lowest, I mean, it exponentially decays down. Okay, and for gamma sub b equal to 0, it is 1 over gamma in here. So I have an exponential distribution for what? For the signal to noise ratio. If my signal to noise ratio is exponentially distributed, what will happen to probability of error? Probability of error always was a function of what? Function of gamma sub b. Is that right? Either it was an ERF complement function or it was an exponential. If it is ERF or it is exponential, I can average that function over this distribution and I'm all set. to just describe that, let's just go for some examples. My probability of errors, the way that I had before, let me first come for average probability of error. The way that I had it before, my probability of error was either something like PE exponential, or it was like PE ERF. And I had two parameters, A in here and B in here. A in here and B in here. Okay? Now, both of them are function of gamma sub B. What I have to do if I want to find average probability of error, I have to average those over my distribution function. Okay. If I come in here for ERF complements, probability of error or bet error, for example, was something like A ERF complement of square root of B gamma sub B. That was what I had for my probability of error. What I have to do now is that I want to find average of this thing, while this thing is an exponential distributed random variable, which has the distribution function of gamma B bar exponent e to the minus gamma sub B over gamma sub B bar. Okay, so do you remember how do you do the averaging? If you have like a function of a random variable, if you want to average it, what you do? I have a function of a random variable like x, and if I want to average it over this, I multiply it with the probability distribution function of x, and I integrate it over dx. If I have function of a random variable like anything, y equals to f of x, and I want to find average of y, what I do is that I take this f of x, multiply it with p of x, which is distribution function of x, and I integrate over. If you want to remember that, go and check the Populis, for example. Okay? So what I have in here now is average probability of error is like A times ERF complement of this guy times probability distribution function of gamma sub B, which is this thing, times this thing. And I have to integrate it over d gamma sub B. That's a very tough integral, but if you check the tables of integrals, it is available there. And the result is something like this. This is roughly equal to. So, but the good message that I have in here is that if you have a Rayleigh fading channel, the average bit error rate is, which is in the form of A ERF complement of A ERF complement of square root of B gamma sub B. That was my error rate on regular non-fading channels. Now, if I go over Rayleigh fading, average error rate is A times B gamma sub B bar over 1 plus B gamma sub B bar. And that's exactly this equation in here. Okay? Actually, it's a very simple equation. If you look at that, gamma sub B is average signal to noise ratio. Average signal to noise ratio is always like 10 dB, 20 dB. That's a large number. Huh? If it's a large number like 10 dB, 20 dB, and B is something like 1, 2, these two multiplied with one another often is much bigger than this 1 in there. But anyways, if you do the expansion of this two, you can approximate it to this thing. That's Taylor series expansion of B over gamma sub B bar over 1 plus B gamma sub B bar. Okay? It will end up to something like A over 2 B gamma sub B bar. Or you can keep it like that, either way. So that's the first one. So my average bit error rate, if I have like ERF complement function, so in summary, if you want to put it, in summary, what I did in summary, I said that if your probability of error was given by a ERF complement of square root of b gamma sub b, now if I go over a Rayleigh fading channel, my average error rate is something like, can be approximated with something like 2 over 2b gamma sub b bar. If I want to sketch that now, this would be like something for gamma sub b. Let's assume these two are normalized to 1 and just sketch that. That's just like a constant which moves my line. At gamma sub b equal to, let's say, 10 dB, for example, this in dB. 10 dB means gamma sub b is what? 10. So this is 1 over 10. So 10 to the minus 1. Okay? Do you follow what I say? If I assume these two equal to 1, for gamma sub b equal to 10, which is 10 dB signal to noise ratio, PE is 1 over 10, which is 10 to the minus 1. Okay? Now, if I come for like 20 dB signal to noise ratio, 20 dB signal to noise ratio means that gamma sub b equals to what? Average. Equals to what? Gamma sub b average is equal to what? Is equal to 100. Okay? 20 dB is 100 times. Okay? So, what is the error rate? Is 1 over 100, which is 10 to the minus 2. And if I go for 30 dB, which is like 30 dB is what? 1,000 times. 1 over 1,000 is what? 10 to the minus 3. So if I sketch it really, it's like a line. My probability of error is like a line. What was my probability of error when I didn't have fading? Do you remember? It was like waterfall. It was like this. A major difference in here. I need a lot more average probability of error to get the same error rates. Okay? So that's the first one. Let me just get the other type of sketches. The other type of sketch that I have now is for the other type of probability of error that I had was what? The second type of probability of error was when probability of error was a e to the minus b exponential, gamma sub b. If I take this thing and do the same thing, find the average over Rayleigh fading, I have to multiply it with e to the minus gamma sub b. This is now poorly typed. In here, this should be e to the minus gamma sub b over gamma sub b bar. This is like this exponential in here. Okay? And if I take this integral, these are just two exponential multiplied. Integral is very simple. Okay? It ends up to this thing. Again, this one is roughly equal to a over b gamma sub b average, which is again a constant, which is 2 times more than this constant, 2 times less than this constant, inverse of signal to noise ratio. So either I have exponential or I have ERF. My probability of error averaged is what? A number, whatever it is, a number, whatever it is, divided by gamma sub b average. Means that if I sketch them in this formal way of exponential for probability of error and dB for signal to noise ratio, I always get lines. So if I want to go from, if I have a line and a slope of the line, let's say, is 1, if this question is 1, okay? If I want to go from 10 to the minus 1 to 10 to the minus 2, I need how much? I need like 10 dB. Okay? If I want to go from 10 to the minus 2 to 10 to the minus another 10 dB, You remember now in those waterfall curves, with 3 dB, I was going from 10 to the minus 5 to 10 to the minus 3. In here, I need how much? 20 dB to do that. Okay? Because in waterfall, I come very fast. If I come from, 2 of these takers, this distance is like 3 dB. But for fading channels, this distance happens to be like 20 dB. This is the main problem, the first problem. If I want to go from 10 to the minus 2 to 10 to the minus 5, I need 30 more dB. Okay? Now, to get still a little bit more specific than this thing, let me just give you a very, very specific example. This is a very, very specific example with binary PSK. This is bit error rate of binary PSK. You remember binary PSK was this, probability of error in non-fading. In fading, it would be like, see, it was A over B, A in there actually. A was equal to 1/2, B was equal to what? Equal to 1. Is that right? That's for binary PSK. If I put those numbers in my calculations, probability of bit error is going to be 1 over 4 gamma sub B average. Do you follow me? Because probability of error average, this one is average. This is just the probability of, was A over B times 2 gamma sub B average, if you remember from last page. That's coming from here. So that's coming from here. Okay? If my probability of error is given by ERF complement function, I can approximate average error rate by this equation. This is what I had last time. I came in here. Now I have my example. My example is binary PSK. For binary PSK, probability of error is given by this. Means that A is 1/2, B is 1. Okay? I get A and B equal to 1. Plug it in this equation. I get this thing. Okay? This is very clear for my example. But I want now to sketch them. Did you got how I derived that? That was very simple derivation. Okay? Now, if I now sketch them, this is the waterfall for non-fading, and this is like linear one for fading. Now look at that now. I'm keen, let's say, on probability of error of 10 to the minus 5. When I'm keen on 10 to the minus 5 is for most of the data applications. Okay? For 10 to the minus 5, in binary PSK, you need something like 10 dB signal to noise ratio if you are non-fading. Now let's see that what happens to the fading. For fading channels, I need 45 dB. What is the difference between the two? Difference is 35 dB. What is the meaning of 35 dB? I mean, just think about it. You're talking about power. 30 dB is 1,000 times. Means that if I had like one radio which had the probability of error with 10 dB and it was just transmitting 1 watt, now if I want to have the same error rate on fading channel, I have to send 1 over 1,000 watt. Means 1 kilowatt. 1 watt is like your basic, like around your basic transmitters, either wireless LAN or whatever. And 1,000 watt is like a radio station or a TV station. It's a huge transmitter. This is the problem with the fading. Okay, how should I remedy that now? So the first observation that I have done so far, based on a very basic and simple example, is that I told you that the difference between fading and non-fading channel is that in fading channels, my amplitude is changing. Then I said that, okay, let's take as example the Rayleigh fading and do some computation. And I calculated the average probability of error on the Rayleigh fading, and then I told you that error rate is now drastically worse. Why this thing happens? That's the first question. The reason that it happens is that, see, this probability of errors, when you go to the fade, deep fades, probability of error goes very, very high. It's something like 0.5. When you come on top, signal to noise ratio is high. Probability of error is like 10 to the minus 10, 10 to the minus 5, 10 to the minus 10, something like that. It's very, very low. When you average 10 to the minus 5 and 0.5, what is going to stay? This is almost zero. These guys are going to stay all the time. So as soon as I go to fade, I make a bunch of errors. And then that dominates the average probability of error. Did you follow the intuition behind it? So when I go from like non-fading channel to fading channel, my error rate goes very high, and I need very high signal to noise ratio, a lot more power. But I want to see what is the source. The source are these fadings. And each time that I go to the fading, I mean, see, 10% of the time, something like that, I go to the fade. And if like 10% of the time I go to the fade and my error rate is 0.5, even if I don't make any errors in there, my overall error rate is 0.5 divided by 10, which is 0.05. It's a very high error rate. You follow me? That intuition is very, very important point to understand the radio channels and how people go to remedy that. So my problem in fading channels is that I go to fade, and whenever I go to fade, I make a bunch of errors which dominates everything. So if I want to remedy this situation, what should I do? I have to avoid the time that I go through the fade. Then I wouldn't need that 35 dB extra. Are you with me? Okay. Now, I want to just continue that discussion. So that discussion is the discussion of diversity. But before I get to that, I would like to talk about my other performance criteria, which was probability of outage. And just talk about that mathematically. What is the probability of outage? Probability of outage, or outage probability, I know that I have shown you this one in here. The physical meaning of probability of outage. The physical meaning is this thing. I have the signal going up and down, and then I have a threshold like this. How do I define the threshold? My customer comes to me and says that I don't want to have error rates worse than 10 to the minus 5. Then I go to that waterfall curve for the modulation technique, and I say for 10 to the minus 5, this is the gamma threshold. This is the signal to noise ratio that you need. Okay? So I come in here and I put that threshold in there. Okay? So my signal is always above the threshold, is acceptable. Suddenly it comes below the threshold. So what I need to do is to calculate the ratio of this thing, I mean the time that I'm under to the time that I'm above. Since my probability of error is a function of gamma sub b, if I want to calculate probability of outage really is integral of this f of gamma sub b, whatever it is, over like distribution function of gamma sub b, which I call it like p of gamma sub b, whatever, from gamma threshold to infinity. That's the probability of outage. Sorry, between 0 and gamma sub. That one is probability of not being in outage. This is probability of, is integral between 0 and gamma sub threshold, because I want the signal to noise ratio to be under the gamma threshold. Whenever it is under gamma threshold, I'm in the outage. The other one was 1 minus outage. Make sense? This of gamma sub b. So basically, again, if I want to formulate this thing in mathematics, what I do is that I come in here. I have, like, let's say, a probability of error, which is given as a function, or exponential function of signal to noise ratio. Okay? If it is given as a function of exponential function of signal to noise ratio, if I inverse this function, gamma sub b would be equal to 1 over b natural log of PE over A. Now, the first step that I do is that I take your probability of error, which was PE threshold, and I put it inside here, and then the gamma b that I have in here would be my gamma threshold. And that's exactly what I have in here. Okay? This is how to calculate from threshold error rate, how to calculate threshold signal to noise ratio. When I calculated the threshold signal to noise ratio, probability of outage is very simple, really. I don't need this function anymore. What I need is this distribution function of signal to noise ratio, which was what? Was exponential in a Rayleigh fading channels. Okay? And integrate that between 0 and gamma sub t over d gamma b. You follow that? What was this f of gamma lambda? That was 1 over gamma sub b average e to the minus gamma sub b over gamma sub b average. And this was for what? This is exponential distribution, which associates to amplitude, amplitude square of what? Of Rayleigh fading. Okay? So as soon as my signal to noise ratio, if I had Rayleigh distribution for amplitude, then signal to noise ratio, gamma sub b, would be exponential. This is something that we saw earlier. Okay? So I get this exponential random variable, I put it in here. I take the integral between 0 and gamma sub t. I end up with this thing. This is my probability of outage. Very simple. And if rather than this gamma sub threshold, I put this value, I will have this thing in there. Did you follow me? So just again, I repeat these things several times just to clarify the thing. But what I said in summary is that if you have, like in non-fading, if your probability of error is something like A e to the minus b gamma sub b, okay? Your probability of error could be something like A f complement of square root of b gamma sub b. Whichever of these two are, I put in here PE threshold, and based on that P threshold, I will calculate the gamma sub b that I will call this gamma sub b gamma threshold. Okay? Then calculation of probability of outage is very simple. Probability of outage is integral between 0 and this gamma sub t, whatever it is. If I have a Rayleigh fading, 1 over gamma b average e to the minus gamma b over gamma b average d gamma sub b, which is equal to 1 minus e to the minus gamma threshold over gamma sub b. This is my probability of outage. In 2 steps, I will calculate. Did you follow that? What is the physical meaning of this, like, probability of outage? This is percentage of the time that my signal to noise ratio is unacceptable. Unacceptable means what? It is signal to noise ratio is below a threshold value that I wanted, or my error rate is worse than certain value that my customer has told me. And I can calculate it as simple as this. Now, for anything it is. Okay? So again, these are calculation. The key of calculation for probability of outage is like the simplicity of, for the Rayleigh fading, simplicity of the integral over exponential function. Okay. So now how about examples? These are a bunch of examples, actually. These are examples for what? Non-coherent FSK. That's coherent FSK. Binary PSK coherent and differential binary PSK. And if you want the probability of error associated to them, that was given earlier in this lecture in here. These are error rates associated to that. Okay. Now, if you get these error rates in here, these were error rate in non-fading channel, and now you want to see what is the outage probability versus, like, this is minus log 10 of threshold, gamma threshold. Means gamma threshold in logarithmic form. Okay, so you get functions of this sort. These are your probability of outage. Apparently, as gamma threshold, you bring it, threshold for signal to noise ratio, you bring it lower, your error rate gets better and better. If you accept higher data rates, it gets worse and worse. Okay? This is just the meaning of probability of outage. So, I gave you, so far, I started with 2 things. I said that if you have a fading channel, and this fading is like Rayleigh fading as my example, numerical example, what will happen is that in order to calculate my error rate, I cannot use the same equations that I was using in chapter 7 for non-fading. My performance criteria now is not error rate anymore. It's either average error rate or probability of outage. Then I looked at the average error rate stuff, and I told you, based on my calculations, here you need something like 35 dB more signal to noise ratio to have the same error rate as non-fading channels. Okay? That was basically summary of what I told you so far. Now, we want to think of remedies. How can I remedy this situation? In order to remedy this thing, the first thing which comes to mind is coding. Why coding is important? Let me just come back to my first curve that I like, so dearly like, that's this one. I'm explaining everything intuitively rather than like derivations. There are a lot of mathematical derivations associated to these things in more details, which are available in John Prokis's book or any other digital communication book. But here we want to capture the equations and capture the intuition. The intuition that I gave you so far was 2 things. One was, if you have fading, for example, Rayleigh fading, your performance drops very bad. And then the second thing that I told you was that this is caused because of these things. Because these fade, because of the fades. Because each time I go to the fade, I make a bunch of errors. While if I'm non-fading channel, I make errors due to additive noise, which is like 1 out of zillion time. Okay? But in here, as soon as a fade comes, a bunch of error comes in. Now, and I showed you that mathematically, and I gave you some structure, and I gave you the physical numbers, like 35 dB for binary PSK. Now, I'm sitting in here, I'm asking for solution. What is the solution? Based on the intuition that I gave you, obviously, I have to find a way to take care of these fades. Means that when I go to the fade, I don't make errors. How can I do that? One of the simplest things which comes to the mind is to use coding. If you remember from your other courses, coding techniques are techniques that in which I can recover the errors by adding some parities. I have error detection codes and error correction codes. Error correction codes, like Hamming, for example, if I have so many number of bits and add so many parity to that, I can correct up to so many bits in them. So codings are very effective. And then I have two types of coding. I have block codes, and then I have convolutional code. Convolutional codes are actually much better in error correction. So I have a sequence of bits like 0, 1, 0, 1, 1, 1, 0, whatever, and I send them, I receive something like 0, 1, 0, and then suddenly this one goes error, goes to 0, and then 0, and etc. If I have a strong, powerful code, theoretically I can change this 0 back to 1. Okay? That's the purpose of coding. I don't want to go into the detail of coding, but generally, this type of coding, error correction codes, convolutional codes are very strong. And also other codes. Okay? Forget about the detail of the code because we are talking about intuition. Okay? So, what if I'm sending my bits over here, I'm sending 0, 1, 0, 1, 1, 0, 1, and suddenly the one which is 0 in here, since there is fade, it gets interpreted as 1. If I code these things while they are going, whenever I go inside here, I recover. Okay? This is a simple case in which whenever I go, my data communication is so slow that every fade only hits 1 bit. So if I have like a coding technique which corrects 1 bit, all set, I'm out of it. But what is governing the rate of variation of these fades? Rate of variation is governed by what? By Doppler spectrum, huh? Or the speed of the vehicle in the cellular, in the mobile communication. So if I'm going very fast, when I go to fade, I may make several errors. If I go very slow, I may make 1. So I need to have different type of coding or some arrangement for that. But basic idea is like this. Coding is very effective to improve the performance over what? Over the fading. Okay? Because in here, when I go through the fade and I make the error, I make that error like the impact is much more because I make it every 10 bits. But if I'm in additive noise channels, I make the error every like 1 out of million bits. In here, I make 1 out of every 10 bits. So if I have like a small code and I can correct that, I can improve the performance much better. This is one of the tricks. Okay? Now, just I can give you some results of that. These are a bunch of codes, popular codes. Hamming codes, BCH codes, Golay codes, Reed-Salomon, Walsh-Hadamard, binary convolutional codes, and turbo codes. And for each of them, we have distances, etc. But I have just a couple of examples to show you the advantages. I mean, this particular one is a good one. It's using a sort of 24-12. Means that you have 12 bits of error parity, okay? And then I don't want to go over the detail. You have soft decision and hard decision coding. Soft decision is that, like, you receive all the samples, you sample them, and you get the entire code word, and then you decide. Hard decision is that every bit that comes, you decide on that. Okay, is much simpler. Hard decision is simpler. Soft decision is a little bit more difficult, but it's more effective. But anyway, in here I have like binary FSK, and then 4 FSK over the fading, and this is when I have the coding in there. Look at that. Like, I was interested in 10 to the minus 5, and with 10 to the minus 5, I had some error rates around, like in here. For this particular signal to noise ratio, I had something like 30 dB, for example, something around that was my signal to noise ratio for 10 to the minus 5. Now that I added the coding, it has dropped to what? Something like 17 or 18. You see that? So the coding has improved my performance like 13 dB. If it was non-fading channel, signal to noise ratio would be something like that. If I do the coding, it would be something like this. Very close to that. And only maybe a dB or something at most improvement. But in fading channels, the same way that fading was killing me. Fading was killing me. Why? Because of these fade hits. Coding is getting me out of that. So this is one of the remedies. So every like radio like communication over severe fading channels, they have a lot of coding in there. Okay? Especially if it is like for mobile type of application. Okay? Why? Because coding actually is anti-fading. Huh? Because fading hits me because when I go to the fade, I lose a bunch of bits. And coding helps me to bring it back. Now, what if my coding is, like my data rate is so like fast that when I go to fade, I have too many bits of error. So the code word goes to error. How can I remedy that? They have the so-called scramblers. So the data comes in, they scramble it. They distribute it over a longer period of time. So that 10-bit error, which occurs like during a fade, it gets distributed over a long period of time. Then they can recover it back. So coding is very, very effective for improvement of the performance. Now, so up to now I talked about two important things. One was fading by itself, and the other one was like coding. The third part which is in there is diversity. Diversity is also, actually coding provides a sort of diversity to the channel. I will talk about that in the next part of the lecture. But in summary, what I did in here, I just described how bad coding can be, and then I told you how good coding, how bad fading can be, and then I told you how good coding can be. Okay? Now, for the next stage, I want to give you another good like news. That good news is diversity, and how diversity is effective in remedy the harmful effect of fading.